I've told you almost nothing, and you were, okay. Temperature 2 is the temperature that it's got, so I'm going to compress it into here. Temperature 2 is the temperature it's got after it goes through a little expansion joint. This has got some name, and I forgot the name of it, but all I did was I took this copper tube and I crimped it down really tight. And so it's going to hiss through this little joint there. Right here is where it expands. So this is high pressure side. This is the low pressure side. And this worked, but it is never, I don't think it's ever worked for a class. It worked before class, but we'll just see if it'll work for you guys. You guys will be special, right? So what do we predict? Where I'm compressing it, the temperature should rise, and where it's expanding, it should actually fall. So temperature 2 should fall, temperature 1 should rise. And all it takes is just a little bit of work, right? Right now it's not looking so good because temperature 1 is colder than temperature 2. Now, I'm standing in for the little electric motor in your refrigerator that every now and then cycles on. It's looking pretty good now, isn't it? Yeah. Definitely temperature 1. I'm definitely generating heat, right? Okay. But we really would be convinced is if temperature 2 would drop. So, there we go. Yeah. Go, Murray, go. Go, Murray, go. This is my new workout. Come on, baby. Yeah. Yeah. Woo! Not so convincing on the cooling side. I'm definitely generating heat. Oh, come on, cool down. Okay. Thank you very much. Kind of dropped a little bit. Woo! Bene vinci refrigeratum. I came, I saw, I refrigerated. Probably not exactly correct Latin. My brother studied Latin. So we would do graffiti. I was a bad boy. We'd use like charcoal, and we write in huge letters things in Latin. I think it's been 7 years, so you can't arrest me for this. Right? We write things like esse quam videri, which means to be, essence, right? As opposed to seeming to be, like video, right? In ceterum cense Carthago delenda est. In my opinion, Carthage should be destroyed. Okay, you see these police officers like investigating this, right? What the? In my opinion, Carthage should be destroyed. Right? We also would like make slings, yeah? Oh yeah. Oh my God, yeah. Slings should be like regulated. Okay, so isothermal, if adiabatic is, it is not an iso anything, right? It should be isoheatic or something like that, right? Okay, isothermal means same temperature. Okay, so with the ideal gas law, we always assumed like if we expanded something and we didn't overtly change the temperature, that the temperature would stay the same. But in general, when you move the piston in and out, I hope I've impressed upon you enough, right? In general, moving the piston in and out involves changing the temperature, doesn't it? Sometimes a lot. We caught something on fire by just moving the piston, right? Okay, I had very impressively changed the temperature of the gas, right? So isothermal means that delta U is 0. That's all it means, right? Here it says delta T is 0, right? But aren't they the same thing? If this is 0, this has to be 0, if you're understanding it right. Okay? So isothermal expansion, let's think about this. Work is done by the gas, right? So now it's like, okay, so we're doing Q is delta U plus work, right? If this guy's always 0, well, let's see if it's an expansion. I've got to erase the refrigerator here. Okay, if it's an expansion, right, and the work is positive, what do we know about the heat? It has to flow in, doesn't it? Yeah. positive heat has to flow in to make it do work without the temperature dropping. Yeah? Okay. Normally the temperature would drop when you expand, so we have to have heat flow in to make it not drop. Does that make sense? With adiabatic expansion, it would drop, but because it's isothermal, it can't drop, so we got to have heat flow in to maintain the temperature so it can do work. Yeah? And then, of course, compression is the opposite. Right? So that's, we've got negative work done on there, right? Okay? So heat has to actually flow out. That's what that means. So with an isothermal expansion, expansion should cool it down. Why doesn't it cool down? Because heat flows in, yeah? Heat is allowed to flow in these processes, right? With a compression, compression should cause the temperature to rise. Why doesn't it rise? Because heat flows out, yeah? Does that make sense? This is, by the way, completely impractical. How can heat flow out without a change in temperature? Heat usually flows because there's a difference in temperature, right? So this is not actually something that you can actually do. It's just, it's important for the mathematics of it. When you study thermodynamics later, you'll actually do some calculus with this. If it's isothermal, it's really easy to plot the graph and do the math for it, right? Basically, isothermal processes, in order for them to happen, have to happen very slowly. I push the piston in, the temperature rises a little bit, but not really very much, right? And then heat flows out, yeah? I push the piston in a little more, and the temperature rises, but not really very much. So you could say it's almost zero, right? But then heat flows out, yeah? And it equalizes again. And I push the piston in, right? So it's got to be like they'll talk in your physics book about dropping grains of sand, you know, one every week on top of the cylinder. It's like, are they doing drugs or what? No, no, they're just saying that it has to be really, really slowly, right? Okay. So compression, blah, blah, blah. Right? Okay, so let's go. What's going on here? Let's look at some graphs. It's isobaric expansion, and how can we increase the volume without having the pressure drop? Should drop. So what's happening? We're increasing the temperature. Heat's got to flow into this thing, right? And the heat is going to two places. It's actually doing work, right? And it's also increasing the internal energy. The temperature has to rise. Okay, so Q flows in, and it heats it up, and it also does work, and that stays level. Okay, heat flows in, temperature increases. What's going on here? Is the piston moving at all? Is there any motion this way? No. So it's not a compression, it's not an expansion, but it's definitely a depressurization, right? So which one is it called? Isochoric, right? Right? Isochronic is when it keeps happening all the time, right? Okay. So anyway, there it is, right? The pressure is dropping. So what's happening to the temperature? Heating up. Is that why the pressure is decreasing? Cooling down, right? Usually when it gets colder, the pressure decreases. We kind of did like a lab or something on that, didn't we?
Just like something.
Yeah. Okay. Heat flows out, pressure drops, right? Uh-oh, we're putting them together. What are we doing? Isochoric, not expansion, but pressurization, right? Then we isobaric expansion. Yes? Is any work done here? Heat flows in, but is any work done? Are we almost near the end of class? Can we be polite and not put our stuff away till, I don't know, a minute before? Heat flows in. Is it doing any work here? No. Is it doing work here? How do you know? The volume has to change for you to do work, right? You have to move this way. The piston has to actually move. It can't just get there and go. It can't just get pent up. It can't just go. It's got to actually move something, right? Okay. Okay. This is. I took this off an IB test. This is the height of thinking about things. Now, on the face of it, you got 50-50 chance, so we'd have to give you a lot of these, you know. So one of these processes is adiabatic. One of them is isothermal. Okay. So which one's which? A is isothermal and B is adiabatic. Why? Because it what? It matched the picture. Yeah, you're right. Adiabatic expansions tend to be steeper than isothermal. Why?